Statistical Rethinking, second edition, chapter 12, and we're just starting the hard questions, so it's 12H1. So all of this here is the question, so you can read it for yourself, and I'll kind of give a summary here. But the idea is that we're looking at the data that was discussed in a paper, and the title of that paper was called "Female Hurricanes Are Deadlier Than Male Hurricanes." So at least in the U.S., I'm not sure about everywhere else, but we refer to hurricanes, they're usually given a first name. And I guess that the names alternate between traditionally male and traditionally female names. I think that's how it goes. But anyway, this paper reported to find that hurricanes with female names were deadlier. And so we're going to examine that claim here, okay? Just on its face, this seems ridiculous, right? Because we give the names arbitrarily, and then the hurricanes develop and do whatever they're going to do. So it seems kind of silly that somehow the hurricane is responding to, whatever we decide to arbitrarily call it. But I don't know the paper. That they may have been trying to make some statistical point. I really don't understand the paper. Or, I never read the paper. But okay, so we're going to do some things to try to examine that claim. So the question asks us to begin by looking at the hurricanes data file here. So I can do that with the question mark and then hurricanes. Oh, by the way, if you have not already, make sure that you have installed and loaded the Rethinking package with all of this code up here. So, okay, so let me go back down. Okay, so first thing we want to do is learn about this data set here with the question mark hurricanes, and then we can kind of look at it right here. Okay, so here we have the first 6 rows. I think this has like 92 total rows or something like that. I don't know, but and we kind of see the variables here, and the ones that we're going to be interested in is number of deaths as well as femininity. So we should probably come to understand these. So first with deaths, I think this one is pretty self-explanatory. It's just the number of deaths caused by a particular hurricane listed here on the left here. And then there is femininity. Okay, and so femininity is a scale of 1 to 11, where 1 is a totally masculine name and 11 is a totally feminine name. And these numbers were arrived at as the average of 9 scorers. So I guess they saw a name and then rated the name of whatever name was given on a scale of 1 to 11, where 1 is masculine and 11 is maximally feminine. So that's how it all goes. Okay. So now the next thing we're supposed to do is to build a model, okay, where we're using femininity as a predictor variable. So the first thing I want to point out is it takes me a second to really get my head around this, but if we're supposed to use femininity as a predictor variable, I'm not really sure that femininity is a numerical variable. Right? It's subjective scoring given by different raters, and so obviously each rater is going to have their own sense of how this should apply. And then also it's not clear that a femininity score or the difference between femininity equals 2 and femininity equals 1 is the same difference as, say, between femininity 11 and femininity 10. Okay? So this already starts to raise the question: is how do we put femininity into the model? Should it go in as a categorical model? But we're saved from having to go through that whole rigmarole because I think, so tell me if you think that this is incorrect, but because femininity is the average of scores, okay, well then by the law of large numbers, if you're not familiar with that, then I suppose look it up because I won't go into it here. But by the law of large numbers, even though these are not numerical scores, or any independent score is not a numerical score, by averaging them together, they approach an actual mean value with an actual standard deviation, and therefore it approaches a normal distribution, meaning we can treat it as a proper numerical variable. Okay. So we're going to fit this model. It says to fit it with an intercept-only model, and then using femininity as a predictor variable. Although we don't really do much with the intercept-only model. So, but anyway, so here we have. Well, so first I organized the data into D and F. D for deaths, F for femininity. Okay. And so we're regressing deaths as a Poisson random variable, where the lambda parameter, or the log of the lambda parameter, is given by this right here. Okay, given by our linear model that has an intercept, as well as a slope for femininity. Okay, and I put some priors on here. I didn't put much thought into these priors. I mean, I gave a little bit of thought, you know. So, but I don't know that it's really critical to answer the questions to answer the questions presented here. But so here's the model. Okay, so I've already ran this, so we don't have to sit here and watch it. And so let's look at what the relationship is with femininity and death. So for that, we go to the Pressey output for MF. Okay, and we see that, well, so here's the entry for the slope of femininity. And we see that, in fact, there is some kind of association, some kind of positive association between deaths and femininity. So as femininity score goes up, there seems to be a positive increase then in number of deaths. Okay, so that's, well, that's whatever it is. Okay, but now we are supposed to. So we just looked at how strong that association was, and it's pretty weak, but it's there. But now we need to go through and we need to examine how well does the model fit or retrodict the data. Okay, so we're going to do that in several ways here. So the first way that we're going to do this is just with the post check command, right, which gives the posterior predictive check or distribution. It plots the data, these blue points, against the predictions of the model, kind of the black markers. Okay, and we see that that the model is doing a terrible job of capturing the data. Okay. In fact, there are more points outside of the 89% credibility intervals than there is inside of them. Okay, so the model is not doing a very good job. So, but let's see which models or which types of storms on the femininity scale may be better or worse predicted. Okay, so I'm going to plot deaths against femininity and then plot the predictions of the model. Right. So here you know, the data and predictions are just given, you know, they're just given, you know, sequentially in the order in which the data is presented. But now we actually want to organize it in terms of, you know, femininity. So I'm extracting samples from the posterior distribution. Okay, and then I am defining. You know, I should really define that as 1 to 11 because that's really what the scores are, not 0 to 11. I hope that doesn't break anything. Okay, that was nice. That didn't break anything. Okay, so I have my scores of F, femininity, from 1 to 11. Okay, and then so first I want to find the mean. I want to find the expected number of deaths across femininity. Okay, and so that's what this code here is doing. Okay, so all I'm doing. So first I'm creating a. There's simpler ways to do this, by the way. But I like doing it this way just so I can see how everything is working. So I have a matrix that I've created that's empty, okay? And then for every column in that matrix, and there's one column for every value 1 through 11, I'm exponentiating lambda, okay? Right here, all right? And so now that's going to give me a great big matrix, right, of about 1,000 rows and 11 columns, okay? And then so for each one of those columns, which is a femininity score, I'm going to take the mean and the PI, the 89% credibility interval, okay? Then I'm going to do something similar. So that gives me the expected value, but I also want to see the variation around the expected value. Okay, and so for that, I'm actually going to simulate deaths, right? This is simulate the expected number of deaths, but now I also need to incorporate all of the variability, okay, in my Poisson distribution. Okay, and so I again build this matrix, but now instead of just finding the expected value, which is lambda, okay, I am generating a random Poisson value with lambda. Okay, so I hope you see the difference, right? So here I'm just finding the expected value, which equals lambda, and here I'm generating a random Poisson value with lambda given by the linear model. Okay, and again, I take the mean and the credibility interval for that, and then I plot it all here. Okay, so so what you see is, so there's a solid line here that represents the expected value, and then there are dashed lines on either side of it, which represents the 89% credibility interval, okay, for the expected value, and then an even lighter set of lines, these dotted lines, that represent the 89% credibility interval for total deaths, not just the expected number of deaths, okay? And then the circles, of course, are the raw data points, and you see just how abysmal the fit is. So our model is not doing a good job at all. Okay. Now there's probably one more way that we can look at the fit or lack thereof of our model, and that's with the k values from the PSIS. Okay, so I'm going to plot the PSIS values. Okay, so first I'm taking the point-wise PSIS scores from the model, okay, and then I'm going to plot them, and then remember that values of 0.5, 1. These are bad values, and so I'm just demarcating, bad to worse values of the k values, with these different lines here. And so this is what we get. Okay, so here's most of the k values, but we see a great number of k values are, around 0.5, greater than 0.5, greater than 1, and there's even one here that's greater than 2. There's 2 observations greater than 1.5. So in other words, again, our model is just not doing a very good job of capturing anything. So the idea that female names are predictive of worse hurricanes is, well, even though our model seemed to suggest that, there's evidence that our model is not a good representation of the actual phenomenon. So, okay, we'll call that good.